Alright, hi everyone. In this video we are going to go over a superposition problem which includes a dependent source. So here's the circuit we're working with here on the left, and we can see the dependent source right here. It is a current source and it has an amplification factor of 4, and it's amplifying a current. Current that it's amplifying is labeled I0, and it's the current that's going from left to right across this 10 ohm resistor. So we can write that in here the way that you might see it in a textbook. So that's the dependent current source. And so the question is saying to solve this problem using superposition. And so as a quick reminder, superposition means you solve the circuit multiple times, and in each iteration that you do it, you only leave on one of the independent sources. So the key there is independent sources. The independent sources in this circuit are these two. So the 5 amp source on the left and the 30 volt source on the right. The dependent source stays in the circuit each time you solve this via superposition. And again, that's because this is a dependent source and not an independent source. So specifically, the dependent source, it's saying that the current that's going from bottom to top across this branch will change depending on what the independent sources are. So to keep it simple, superposition of a dependent source is just like the same way that you would do any superposition problem, except you leave in all the dependent sources in each iteration of the problem that you do. So far we've identified that there are two independent sources, and so that tells us we have to solve this problem twice. Once for each independent source. And so we'll go ahead and start with the 5 amp source. So I'll redraw this circuit with just the 5 amp source in it, and I like blue, so let me change the font color. So there's the 5 amp source, and then here's a 40 ohm resistor that it goes through, and then here's a 10 ohm resistor that it goes through, and then here is that dependent current source, and then here is a 20 ohm resistor. And notice that I'm being funny. I'm instead of putting it on the top, I'm moving it over to the side. And the reason why I'm allowed to do that in this case is because we've turned off this 30 volt source. If you turn off a voltage source, that's the same thing as shorting it. And so in this case, when you say shorting, it means you're replacing this with a wire. So here's the 20 ohm source. I could have just as easily actually draw this out so it's a little more clear. So here's the 20 ohm source. That 30 volt source is being shorted out or turned off, so it looks like that. So what I did earlier was I sort of moved that 20 ohm resistor over here, and that's completely fine to do because it doesn't modify the voltage and current characteristics of the circuit. So I just got to make sure I get rid of that. There we go. So this circuit is exactly the same as above, except the 30 volt source is turned off. So we'll go ahead now and solve the circuit. And so in this case, by the way, we're trying to solve for I0 and V0 ultimately. So we'll start here with this iterative circuit, starting with that 5 amp source. So again, this is what the circuit would look like if you were to turn off the 30 volt source. Okay, and we can solve this using either nodal analysis or mesh analysis. And generally the way you choose between them is you count up the total number of nodes, you count up the total number of meshes, and then if there are fewer nodes than meshes, then you'll do nodal analysis and vice versa. So in this case, there are a total of 2 nodes that I see. If you don't include ground, you never include ground in nodal analysis. So there are 2 nodes, one here and one here, and there are 3 meshes. So there are 2 nodes, 3 meshes, so it seems like you might want to do nodal analysis, but you can see that there's a current source in one of the meshes, and here's another current source in one of the meshes. So you actually have 2 super meshes as part of this problem. So that kind of reduces the 3 that we started with to 1. So it might be a better choice to do mesh analysis in this case, because 1 is less than 2. So we're going to do mesh analysis. We'll draw in all the currents, or rather all the meshes we see, so there are three, we give them names, I1, I2, and I3, we can see right away that I1 is equal to 5 amps. And that was the benefit of using mesh analysis here. We saw that there's a current source, so we don't actually have to do KVL around this I1 loop. We know exactly what I1 is right off the bat. Now we'll go ahead and do the I2 mesh, but we see that between I2 and I3 there's a dependent current source, meaning this is a super mesh. So instead of writing out separate equations for the I2 loop and the I3 loop, we write a super mesh equation for the combined I2 and I3 loops, which we'll draw here, this circle path here. So we'll start with that 40 ohm resistor. So that 40 ohm resistor, it feels I2 and I1 minus I1 because I1 is opposite to I2. The next one is the 10 ohm resistor, which only feels I2. The next one is the 20 ohm resistor, which only feels I3. And we set this whole thing equal to 0 according to KVL. So we have two equations, three unknowns, so we need one more auxiliary equation, and we'll get that from this current source here that forces us, or that this current source here that told us to do super mesh. So we always go back to the source that is helping us. So we come back here and we see that this current source is going upward, and you'll notice that I3, if you expand it, is going upward as well, whereas I2 is going downward. So you can write out your final auxiliary equation as 4 times I naught, which is the dependent current source, is equal to I3 plus I3 because it's in the same direction as the dependent source, and then minus I2 because it's in the opposite direction. So there's your third and final equation. We'll plot that here, and then you can solve this in MATLAB or Python. We're not done. Remember, we have to solve this circuit twice. Once for each of the independent sources, so we'll sort of scoot this off to the side for now, and we'll do the second circuit now. This time we turn off the 5 amp source, so if you turn off the current source, it's like you're opening the circuit here, meaning that current can't go from the bottom to the top, so you're literally removing a piece of wire. So what that'll look like is, let me redo that, so here's the 40 ohm resistor, and that 5 amp source used to be here, but it's gone now because you opened the circuit, i.e. you turned off the 5 amp source. Here's the 10 ohm resistor. Here's the dependent current source, 4 times I naught. And by the way, remember from here, I naught is equal to I2. You can see I2 goes in the same direction as I naught. And so there's I naught is equal to I2. And you'll need this in one of these equations down here, which references I naught. So really there are 4 equations, 4 unknowns here. There they are. We'll come back here now, and we'll draw this in this time. There's the I naught. Okay, and we'll continue. The next thing is the 20 ohm resistor, and then here's the 30 volt source. So let me draw that slightly differently. So negative, positive, 30. There's the ground. Alright, so there are 3 nodes, 2 meshes. In fact, there's a super mesh here, so it's going to be a wise choice to do mesh analysis in this problem, because there are much fewer meshes than there are nodes. Okay, so we see a total of 2 loops. We'll give them names, the I1 loop, the I2 loop. Again, we're doing mesh analysis. We notice that there's a dependent source in between 2 meshes, meaning we have a super mesh. So instead of writing out separate equations for the I1 loop and the I2 loop, we'll do one big equation for this super mesh, which I'll trace using this yellow highlighting here. Okay, so we'll start with the 40 ohm source. It feels the I1 current. And then we go to the 10 ohms resistor, which feels the I1 current. And then we go to the 20 ohm resistor, which feels the I2 current. And then we hit the 30 volt source from the negative terminal. That's why we put the negative sign here. And then we've completed our loop, the yellow loop. So we set this whole thing equal to 0. Notice that we have one equation, 2 unknowns. The 2 unknowns are I1 and I2. So we need one more equation. Just like earlier, we're going to get it from that circuit element that's helping us, that provided us the super mesh. So right here with this dependent source, we see that this dependent source is in the same direction as I2, whereas it's in the opposite direction as I1. So what we'll write is that 4 times I naught, which by the way, again, I naught in this case is equal to I1. You can see I naught goes in the same direction as I1. So this is the same thing as 4 times I1, which is equal to I2 minus I1. So I2, positive I2, because I2 goes in the same direction as the dependent current source, minus I1 because it's going the opposite direction as the dependent current source. So this is our final equation. We'll grab this, grab that, we'll paste it down here, make it a little bigger. So now you have two equations, two unknowns. And you can solve this, MATLAB, Python, by hand, whatever you like. And ultimately what you'll get is an answer. So from this circuit here, the answer that you care about is I1. And the reason why is because in this case, I naught is equal to I1. So again, really what you care about is I naught. I naught is equal to I1 in this circuit. For the previous circuit, I naught was equal to I2. Therefore, from this set of equations, what you're ultimately trying to solve for is I2. So once you get those answers, what you do is you say, oh, well, the total current, or rather, I'm going to say total I naught. So I naught, once again, is that current we were ultimately trying to solve for from the very beginning. So I naught total is equal to I1 plus I2, which is the I1 is the contribution to I naught due to this 30-volt source, and I2 is the contribution to I naught total due to this 5 amp current source. So you add those up and you get I naught total. And this is half of the answer. So now you've got this. You've got that, that's equal to I naught total. So now if you want to get V naught over here, well, that's pretty simple. You use Ohm's law, so V naught is equal to the 10 ohm resistor times the current through it, which is the I naught total. And then you get your final answer that way, and then you can compare to this answer key shown here. So you can see the total current going through the 10 ohm resistor is 1.533 amps, and you can see the node voltages on the left and right side of the resistor, subtract them, and you can get the voltage drop, which should be equal to this. Alright, thank you.